Now let us study the a priori algorithm, which is based on this principle that if the anti-monotone property, so if a set is infrequent, its superset is definitely infrequent. So what we do is that if we have to illustrate in the same the lattice diagram that shows all the candidates, we can see that the moment we find that AB is infrequent, we can prune this entire bounded subset of the lattice. So we can remove all the candidates, and we don't need to measure or estimate the support for each one of them. So this will significantly reduce the computations that are required for finding out the frequent item sets. So now, how does an a priori algorithm work? A priori algorithm is for candidate generation and test approach. So it uses the pruning principle, that is any item set is found to be infrequent, its superset should not be generated or tested for the support. So the way it starts is that you first scan the database and find out all the items which are frequent, which is we refer them as generalized one item set. Using our nomenclature of k item set, to start with, we'll find out all one item sets, and we will find out which are frequent. So we can find out frequent one item sets. Then from each k item set, we somehow generate k plus one candidate item sets, which are all potentially frequent. And this is not to say all k plus one item sets will be frequent, but we will only generate those k plus one item sets which have potential to be frequent, not all. So in this case, this does not have potential to be frequent because AB is infrequent. So ABD has no potential to be frequent. But let us say DE is frequent. Then CD is potential to be frequent, because there is no other parent of CDE which is infrequent, because CD is coming from CD, then CE and DE. All three of them are found to be frequent, so we will generate CDE as a candidate, and then we evaluate its support. And still, CD, CE, DE are frequent does not mean that CDE is also frequent. So we need to estimate separately its support and determine whether it is frequent or not. So we will generate k plus one candidate item set from k frequent items. Then we test the candidates against the database and terminate when no frequent or candidate item sets can be generated. So it is simple steps. So so this is the putting it more in a formal pseudocode type of format. So this is like start with k is equal to 1, generate frequent item sets of length 1, repeat until no frequent item sets are found. So generate k plus 1 candidates from k frequent item sets, and if we can somehow prune some of them, because we can somehow conclude that they cannot be frequent, prune them, and for remaining candidates count the support and eliminate the candidates that are infrequent, and so thereby from k frequent item sets we can generate k plus 1 frequent item sets. So let's take the example and do it. So this is how. First step is that given this is the transaction database we are using, we will find and we have decided that the support threshold is 3, or 3 out of 5 is 60%. So we want to find support for bread. So it is there in transaction 1, transaction 2, transaction 4, transaction 5. So that means it is 4 out of 5. So this is 4. Similarly, we find all, and then we use the threshold 3, that is 60%, to say that this should be eliminated, and this should be eliminated. So beans and coke cannot be frequent. So any superset containing beans or coke need not be eliminated, or need not be evaluated for the frequent item set. So given that we can find one item set, how do we generate two item set candidates? And similarly, given two item sets, how do we generate three item set candidates? So here we can use the approach of two-step approach, which is self-join followed by pruning. So how do we calculate, how do we do the self-join? Suppose that, let us take an example. We have the a item 3 frequent item set, which we can refer to as L3. L3 is representing 3 frequent item sets. From this, we need to generate L4, or the candidates for 4 frequent item sets. So we need to generate those candidates. So now ABC, ABD, ACD, ACE, BCD, these are all frequent. So now let's start self-join to first generate some candidates. So let's do self-join of ABC and ABD. So what do we get? ABCD, right? Then we do self-join of ABC with ACD. So what are we going to get? We are going to get the same ABCD. ABC with ACE. So we will get ABCE. Then ABC with the BCD. So that will give us again ABCD. Similarly, now we do ABD with ACD, it will give us ABCD. ABD with ACE. So this is giving us ABCDE. So this is actually, it is becoming 5 item set. So maybe we will not even bother about it now, because our intention is to find out all 4 frequent item sets of size 4. Then ABD and BCD, it is going to give us ABCD. Then ACD and ACE, it gives us ACDE. ACD and BCD, it gives us ABCD. ACE and BCD, it gives us ABCDE, which is 5 items. So now let's see. Okay, so these are all the candidates that we generated through self-join. So before evaluating the support for some of them, because we know the a priori principle, let's see if we can prune some of these and don't evaluate their support. So let's take ABCD, ABCE. What are all the possible subsets of ABCE? ABC, ACE, ECE. Okay, I think that's all right. ABC, ABE. Right. ABE. Looking at this, we can recognize that ABE is not frequent. Okay, ABE is not frequent. So what it means is that this cannot be frequent. ABCE cannot be frequent. Now, similarly, we can prove that ACDE is not frequent because ADE is not present. So that way, we ended up with only one candidate, 4-item set, and we need to find the support for this. So thereby, we could reduce the number of comparisons that we need to do in order to evaluate the support. So this is significant improvement over the brute force approach. So all we used is a priori principle, where we know that support for superset is never greater than the support of its subsets. So having generated, now we know how to generate the support for 1-item sets. Just directly count. We can't do much tricks or techniques here because most of the algorithms at 1-item set level, they simply say that you just have to find out through diligent way. So for bread, we find out the support for Coke, we find for milk. So we simply scan the database and find. So it is possible that one thing that we can do, instead of doing multiple scans, we in one single scan is enough, where we formulate this table, where we keep adding the items, new items, whenever we find that the item already does not exist in the table. And if the new transaction contains one of these items, we increase the support count. So in one database scan, we can generate this table. Okay. Now from 1-item sets, we need to generate 2-item set candidates. So what we can do, bread is frequent and milk is frequent. So we will consider bread and milk together as a 2-item set, and we will see whether it is frequent. Similarly, we can do with bread and butter, bread and diaper, then milk and butter, milk and diaper, butter and diaper. So given that there are 4 frequent 1-item sets, we got 6 candidate item sets of size 2. So how did we get that? This is 4C2. All right. So we got 6 candidate item sets. So at this point with 1 to 2, even if we do the subsetting, because we will be there cannot be a scope for pruning at 2-item set level. Now we have to evaluate the support for each one of them, and now what we recognize is that this is infrequent and this is infrequent. So now we have got 4 2-item sets which are frequent: milk, bread, diaper, milk diaper, butter diaper. So now from them we need to generate the 3-item sets. So let's see, bread, milk, and bread diaper, bread, milk, diaper. Okay, so we got 1. Then bread, milk, and the milk diaper, bread, milk, diaper. We got that. Bread, milk, butter diaper. So this is a new one. But the problem is this is a 4-item set. So we will keep it pending. So then next we will find out bread diaper and we combine it with the milk diaper. So what we are getting is bread, milk diaper, bread diaper, and and butter diaper. So we are getting there bread, okay, bread diaper and butter diaper. Then milk, butter, and butter diaper. So that will come to butter, milk, diaper. Okay. So now let us see uh, whether we should find these support count for these. So what we will do is that we will avoid this because this is of size 4. So we will avoid this. Now let's look for the other. Bread butter diaper. Bread butter is not part of, has a support of only 2. So bread butter diaper can never have the minimum support that is requirement. So that is 3. So we can eliminate this. So this we do not need to count the support for this item, bread butter diaper. So now let's look at milk butter diaper. Milk butter diaper. So we need to see diaper and milk and butter has support of only 2. So what it means is milk butter diaper cannot have the support of minimum support required. So thereby we are ensuring we could see that at 3 item set level there is only one candidate. So what it means that it stops there. So we will not have any 4 frequent item sets given the support count of 3 in this transaction database. So now let's see what are some of the challenges with counting the support. Support counting can create problems for several reasons. One can be that the total number of candidates can be very large, and the other possibility is that a transaction may contain many candidates. So now what happens is that for each candidate, we need to read the transaction and we need to do the support count. Or for each candidate, we read the transaction once and calculate the support for each one of these candidates. As we can see, for a large database, the number of candidates is very large. So what it means that for counting support for each one of them may itself can become a tedious task or can be a time consuming task for the machine. So that is to say we take Walmart database which has got billion people buy every day from there and buy some things, and then we want to find the frequent item set. So from those billion transactions we need to find out so many candidates because they also have million items stocked in their store. So in such case, we need to be concerned and we need to find a way to increase efficiency in every possible method. So one technique we can do, which is a favorite technique in the computer science domain, is to organize the item sets in the form of a hash tree. So that hash tree itself can be generated using numerous techniques. We will find out one technique, but there can be alternate techniques to create those hash trees. Our idea of looking at a hash tree is just to see how that can help us gain the performance advantage by reducing the number of comparisons that are required for the support counting. because there may be a possibility that we can somehow decide that this transaction will never find this candidate based on some criteria. So why not take that advantage and reduce the number of support counting and thereby improve the efficiency of association mining. So the hash tree, to describe it, we will look at the diagrams of hash tree in a short while. But hash tree, it is going to be a set of ordered items. First thing is that each item has to be ordered. So the ordering can be done in several ways. It can be an alphabetic order, it can be a numeric order, because an item can be represented by the number, item 1, item 2, item 3. So each item, they may be having a product code, which is a number, and then that is used for each item in the transaction. So for those numbers, we can easily create the ordering, which is in the order of increasing order or reducing order. So first thing we do is that whenever we have got item sets, we organize them into a ordered item sets and then store them in the hash tree. What we do is that hash tree will have the leaves. We store the item sets and the counts in the leaf nodes, and interior nodes contain a hash table that divides the items. Where given an item set, it decides that in which path it should go and reside in that tree. And this will also require for us somehow to a mechanism whereby we can find out the candidates for the transaction. What are all the candidates that are supported by the transaction? So let us take a very simple store which sells only 9 items, and let us number those items as 1 to 9. So the product code is 1 to 9. So what can we do here? We can sort those numbers 1 to 9, and we can so all the transactions we can sort them, and so that the items appear in an order. And then what we do is that we look at the candidate item sets which are of the size 3, and we will see how to organize them into a hash tree so that the support counting is becoming efficient. So the hash function we use is mod 3, which works well if you have 9 items which are the store is selling. But if the store is selling million items, so obviously 3 will not be a very efficient choice for building the hash tree. If we want to use still the mod function, the number we will use will be possibly mod 999 or something which is going to significantly differentiate the possible item sets. So now, just for the sake of examples, so what we are doing is we are organizing 3 item sets which are so how they would have come, they would have been come from 2 item sets, and then we would have done self join and prune. So finally we ended up with 3 item sets. So this 3 item set, if I have to enumerate, so this is the item set. let's say this is the candidate 3 item sets we got through self join and prune from the database, and we knowing that there are only 9 items sold by store, so that can occur in the transaction. So what we have done is that we have chosen mod 3 as a function to divide the items and organize them at leaf node level. So the mod 3 can leave us a reminder of what? It can leave us a reminder 3 possible values 0, 1, 2. If the reminder is 0, we put it in the rightmost branch. So that is our first choice, that 1, 2, 0. That's the way we organize the tree. Leftmost is 1, middle one is 2, and then the right one is 0. So every time we look at a candidate, we are going to organize, put it into one of the leaf nodes. And what we also propose is that for this one, the maximum leaf node, or we call leaf node capacity, is 3. So we can keep at most 3 item sets in a leaf node. So that is what we have arbitrarily chosen. Because when we define a tree, for each node, some memory has to be allocated. So we cannot arbitrarily say that every tree we want to give infinite size memory. So that will be inefficient. So we need to allocate the space. We are allocating 3, capacity of 3, and beyond that we need to go down further and generate a next one. So now, given these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15 candidate 3 item sets, we'll see how to organize. So 1, 4, 7. So these are the items which will generate a reminder of 1. So we need to traverse in the left branch. So for the first item set, let's say 1, 4, 5. First we will check the item 1, first item in the item set. And what is the reminder 1? So we decide to go along the left branch. Then we will see that in the left branch, the next item is 4. For next item 4 also we are saying that it is left branch again. So for this one we use 4, and then we set up a node here. So actually this is an intermediate step. To start with, the node would have been here only, but the depth will increase as the node gets overflowing. And so that is to say, if I have to take this whole thing. Okay, I think I can transfer this somehow. Okay, so what I have to do is, let's say 1, 4, 5. Let me take 1, 4, 5, 1, 2, 4. 4, 5, 7. To start with, we'll do for this example subset. So what we are doing is that to start with, this is the root node with with to start with, This is the root node with no items. Then we find that 145 comes. So from root node, we are going to the left and we are creating one. So what we are going to store here is 145. Okay. So then comes 2 4s, 124. This will also go by the same. So we are going to have now then next 457 comes, that also comes here only. So after that 457, 125 comes. Okay, 125 comes. So now when the 125 comes, this node is overflowing because this has already got 3 items. So we need to generate the next level. So to generate next level, so what do we do is that, so we create here another intermediate node, and from here when we are going to this, so we are using, instead of the first item, we are using the second item. So that is 4 2 5, because the first one is not going to give us any differentiation. They all give a same reminder, right? So the reminder is 1 with all of them when you use the apply the mode function. We will use the second one. Second one, when we use the reminder, so we are getting 145, we are getting a reminder of 1. Then what we do is we will 124, it is giving a reminder of 2. So what is happening is here 145, here 124, then also 457, we are evaluating the reminder for the second item. So 457 will also come here. Then 125 will also come here. So we had to generate an additional level. And as it happens, when more items come, because there are in this branch there are 5 items, so we needed to go one level further down because a leaf node can have at most 3 items. So this time we needed to use the third item. So 4 and 7, these are the other to the left side, because first and second ones are already used up. Third one, 4 and 7 is putting it in the leftmost branch. 5 and 8, reminder 2 is putting in the middle branch, and 9, reminder 0 is putting it into the right branch. So that way we construct the complete candidate hash tree. So hash functions are generally very fast, and once constructed, once we generate, given that this hash tree will be entirely staying in the memory, because all the candidate item sets, we expect that they stay in the memory. So now comparison with the transaction, we will see how it is going to give us benefits. But then first thing is that we could organize it in such a form so that we could differentiate the candidate item sets and put them into different leaf nodes. That is first thing that we have done. So this is the same tree. It is showing how the second reminder 1 has been used for generating the some of those locations. So reminder 0, which is used for some of the other candidate item sets. Okay, what is the practical usage of hash tree? So this is the question. So do we have a microphone? We can talk. Do you have a microphone, or maybe I will unmute you and let me see whether I will be able to hear you. Mr. Hrishikesh, you can speak. Do you have a microphone?
Yeah, can you hear me, sir?
Yes, I can hear you.
Yeah, so I just wanted to understand what is the practical usage of
Yes,
hash
yes.
tree.
We'll come to that. So what we will do is that you can stay unmuted. So we will go to the next slide. Here we have a transaction. Okay. See, what happens is that we have a transaction database, which will be somewhat like what we have seen earlier. A transaction database will look like this, right?
Yes.
But we are talking about items for which we are not storing the names, but then item numbers. Okay. So item numbers means the transaction will be looking somewhat like this. Let's sorry, item bread is one, and so bread is one, diaper let's say two, butter is let's say four, bean is five. Okay, we already said milk is two, milk is what, three. Okay, so milk is three, so diaper we have given two, then we have given butter as four, coke as six. So we have given the product numbers. So suppose that we have got the database organized like this. So then they'll fit in with the hash tree. So once we get each transaction, we have to see how it is contributing to the support count of each one of the candidates. Okay. See, if we do not organize it well, then what we have to say is that for each transaction, we have to compare with each item set. Suppose there are 5 items in the transaction and item set size is 3. So it is possible that we need to make 15 comparisons before we can decide whether the item set support is supported by the transaction. Have I explained to you? Is that understood? We have to make 15 comparisons because the transaction has 5 items and candidate item set has 3 items.
Yes, sir.
Yeah, so because the comparison itself is costly operation. For example, when we are looking at very large databases, that can be significant. So we are seeing whether we can avoid comparisons for some of the candidates with the transaction, because somehow we determine that this candidate can never occur in the transaction. So that is our intention, and we will see whether hash tree can help us. Okay.
Okay.
So now let us come to this transaction. So transaction has 5 items, 1, 2, 3, 5, 6, and we want to see whether which of these candidate item set support will be increased because of this transaction. So first, what we will do is that because this is organized as a hash tree and the item sets are all ordered, so what we do is that the transaction itself will order. So that we take for granted that we do that. So that is a single sort operation on each transaction to keep it in an ordered base. Or we can say that the transaction database is ordered and stored once. So anytime we do the operation, we will always get the transaction which is ordered. So now 1, 2, 3, 5, 6. So first thing we recognize is that the 1 is present in this. So first item 1. So what it means that this 1, 2, 3, 5, 6 we send to this side on this node for evaluation. But then 1, 2, 3, 5, 6 need not be sent to this side because 1 can never occur on this side. Is that in this branch? Is this fine? So 1 can never occur in this branch. So we can send the simply partial transaction 2, 3, 5, 6 to this branch. Can you see some efficiency gain?
Yeah, I understand.
And then for this branch, 1, 2 can never occur. I will send only 3, 5, 6 in this branch. Okay. So we are not doing a brute force counting. We are trying to do a smart count. So we are reducing the transaction as much as possible when we are sending to the branch. That is point 1. So 1, 2, 3, 5, 6 comes here. And in this side, we will see that 1, 2, 3, 5, 6. So we needed to evaluate, and we come to 2 that cannot be, and 3, they will not be there. So we will send here only 5 or 6, but 5 or 6 do not match because here 4 has to be there to go by this path, and then we recognize that there is no point in sending it further. Okay, so we recognize that this need not be counted. Okay, because 1 we have come here, then we see 2, 3, 5, 6. So we will never be able to go through this branch because to go by this branch we require 4 or 7. So we will see that this need not be counted. Okay, then next we got 2. So we need to send it through this branch. So we will send to this branch 3, 5, 6. Okay, and also we will see that 3, 5, 6 has to be evaluated and 6 has to come. So we'll see that 3, 5, 6 has to be sent by this branch. Then we see that this side only for 3 it will be coming this side. So that is so 5, 6 have to be sent to this side, right? So this is coming to this side, which is 5, 6, and on this side we are sending 3, 5, 6 or 6, but then 6 is subset of 3, 5, 6. Actually 3, 5, 6 itself is good enough. And then after having come this way, so let me see whether it is there. So then we recognize that 3, 5, 6 cannot go in this branch. So we need not consider this. So 3, 5, 6 are potential in this and this. And similarly 1, 3, 6 is potential because we can see that 1, 3 are here, and so this is potential. And this we will use for doing the support count because after 2, this is the only node we have with 2, and there are 3, 5, 6, so it is possible that it is required. Then 3, 5, 6 we come this side, so this need not be done because 5, 6 cannot come into this branch because this can only 4 or 7 can come this way. Then this branch we have to come because this is 5 is occurring, so this can this branch is potential, but it is 5 and 6. So we recognize that 5 is taking through this path, and only 6 is left. So to go by this path, but we see that there are no more items. So that is at most 3, 6 will go this path, but we know that all the items are 3 item sets. So this node need not be visited. So we could see that we avoided visits to 4 nodes, right? So that is an efficiency gain. And then, so we visited out of these 9, we visited only 5 nodes instead of 9 nodes. So that means we have done the transaction comparison with the 9 candidates instead of 15 candidates. Is this understood why we did this?
Yes, sir.
Okay, so we could see that there is a gain, and this gain can be significantly more. Suppose that we have 10 candidates of size 4, and then we have a huge hash tree which is having some 20 nodes, but we know that only 5 of those nodes have to be visited. So it depends on the various situations, but we can clearly notice that there is an efficiency gain. I am muting you now. All right? So now this is all about the hash tree. So okay, we have already recorded for 40 minutes, so let's take break for a couple.